Alright. My name is Jacob Scott Weber, and I've been tasked with explaining and performing problem number 4 on the second homework for Physics 361, Section 1, Semester 2014 Spring. Instructor Warren Christensen. Anyway, okay, so problem goes like this. We are given a finitely sized, two-dimensional, circularly symmetric disk. And the disk has radius, big R, and it has surface charge density, sigma. Surface charge density is, of course, the charge per unit area. The units will be significant. Now, what we want to do is find the electric field, or at least the magnitude of the electric field, at a given point along the vertical axis that extends perpendicularly from the center of the disk at a distance z. And that can be negative, but I'm just drawing it here positive. And yeah, so how do we do this? Well, first thing we want to look at is Coulomb's law, which gives us the general rule for finding the electric field at a given point based on a space of charge density. Coulomb's law is that the electric field can be expressed as an integral over a space filled with charge of dq, which is the infinitesimal of charge. So, imagining tiny little charges being represented by dq, and the magnitude of those charges being represented by dq, over 4 pi epsilon naught, where epsilon naught is just a physical constant of the universe, times r squared. Now what is r? R is the magnitude of a vector. Now this is just the magnitude. If we want to know the actual okay, whatever, the actual vector, we would have to take magnitude of r to the third power and then stick a regular r up on top. But no, well, that is important. I was going to say we can forget about that, but no, this is actually important for what we're going to do. Okay, so first thing we need to do is we need to find what dq is. Now, in order to do that, we're going to divide the disk up into infinitesimal segments, and we're going to multiply the magnitude of those segment sizes by a given charge density that we are given for those tiny little segments. Now we've got circular symmetry, so things become super easy. Let's see, we've got some little segment of the disk right there. And we want to find dq, which is the charge on that little segment of the disk. Let's zoom in. Okay. Alright, so the length of this segment is just dr. It's just the infinitesimal of the radial distance. The width is slightly more complicated. The width is r times d theta. It's not just d theta, theta being the angle going around. It's not just d theta because as you go further out, any given segment of angular width d theta will be larger and larger and larger as it goes outward according to a factor of r, which is to say how far away it is. I should mark that, by the way. This is little r, the distance out there. By the way, don't confuse this r with that r. I'll explain what that r is in a moment. So, length dr and width r times d theta. Now, if we take infinitesimals, in other words, if this segment is sufficiently tiny, we can neglect this curvature and we can approximate this segment as simply a very, very tiny rectangle. And the rectangle will have area r times dr times d theta. And if you take the area and you multiply it by the charge per unit area, you get the charge over that segment. Bum, ba, bum. Sigma times r times dr times d theta equals dq. Well, we can just put that up there. Now we're going to get something really nasty over here, aren't we? Alright, let's try this out. Alright, now before we go any further here, we got to know what this is. It's not just this. This is specifically the distance from the point where dq is found to the point where we are evaluating the electric field. By Pythagoras' theorem, let me box this off so it's separate from everything else. By Pythagoras' theorem, we know what it is. It's r squared plus z squared to the 1/2. That's that distance. So, let's put that down there. Z squared plus r squared, yeah, whatever. But remember, it's to the 3rd power, so it's not just the 1/2, it's to the 3 halves. And then on top, we got this thing, but we've also got one more thing. Well, actually, I'll explain that right now. A vector, of course, has multiple components, and we're looking for the magnitude of the electric field, so presumably we would need to find each component and then use more Pythagoras to find what the magnitude was. But we're given a situation with circular symmetry, and when it has circular symmetry, all of the horizontal components of force cancel out. For every bit of horizontal force pushing this way, there's an equal and opposite bit of horizontal force pushing this way. So all of the horizontal components cancel out, which means that the magnitude of the total force is going to be equal to the magnitude of just the vertical component. And the vertical component is z. So we're going to put z for our hat, our arrow, whatever you want to call that. And so we're going to end up with sigma times r times z times dr times d theta. Now that looks even nastier. It's a horrible, horrible integral. But there are some simplifying assumptions we can make. Well, not really simplifying assumptions, but we can make note of something here, which is that there are no thetas in there. There's a d theta, but there's no theta. And because there's no theta, the integration with respect to theta is super easy, because this whole integral just becomes a constant. And so it becomes... God, I'm hungry right now. Okay. Oops. There's the dirt. It just becomes this. Probably shouldn't be leaning on this board, but whatever. I'll stop. Just becomes that. All of the theta stuff goes out. And note, there's now a pi in both the numerator and the denominator, so we can get rid of those. These can be simplified. This just becomes 2. Now, still looks very nasty, and of course, it is a nasty integral, and you have to be good at doing integrals to find the solution to that. You could just plug it into Mathematica. I happen to know just by inspection what the result of this integral is, but you shouldn't necessarily be expected to be able to figure that out just by inspection. In any case, the indefinite integral of this is going to be, let's see, negative sigma times z over 2 times epsilon naught times that should be correct. Because if we take the derivative with respect to r, this is just a constant, it becomes this to the power of -3/2, that's good, times r times 2 times -1/2. So yeah, this should be correct. But that's just the indefinite integral. Obviously we've got to take into account the limits of integration. So, okay. Now it's negative, so we can just reverse this and get rid of the negative sign. So it'll be from r to 0. So starting with 0, it'll be sigma times z over epsilon naught times 2. Oops, I reversed that. Oh well, whatever. Times, well, where little r goes to 0, it just becomes z squared to the power of -1/2. But, simplification. Z to the -1, which is 1 over z. Z times 1 over z is just 1. So at the first limit of integration, it's just going to be sigma over epsilon times 2. And then at the second one, it's going to be z squared plus big R squared to the -1/2. Because, of course, big R is our other limit of integration. Of course, simplification goes on, so I'm just going to mess up the whole order of this. Okay, now that's perfectly straightforward, it's completely analytical, but there's a problem with it, which is that we can't analyze the behavior quite yet. Remember, the second part of problem 4 is that we have to analyze the function's behavior as z goes to infinity and as z goes to 0. Now we don't want to just take the limit, because we're not just looking for the value of what the field is, we want to know the behavior, which is to say how the function approaches its limiting values. So what we're going to do is we're going to take z over r to 0 to represent when z is much smaller than r. And we're going to take r over z to 0 to represent what happens when r is much smaller than z, which is to say when z is much, much bigger than r. When z is very, very large, close to infinity. So we have to translate this function into terms of z over r and in terms of r over z. So, let's divide the entire interior of this by r squared, so it becomes that. Now we gotta make sure to bring it out back. Now this, of course, is r to the -1, which is 1 over r. 1 over r times z is z over r. And what do you know? Convenient little thing right there. So then it becomes z over r. So once again, we've just replaced everything with z over r. Times sigma over epsilon naught times 2. Okay, so we got this cool thing. Now, if we take z over r to 0, then we just, this becomes 0, this becomes 1 minus 0, which is just 1, and then it just becomes, the whole thing goes to sigma over epsilon naught times 2. Now, that's good. That's what it's supposed to do. Because remember, if you get really, really close to the disk, if z is close to 0, the disk appears to be an infinite plane of charge. It just goes out in all directions indefinitely. And it becomes an infinite plane, and an infinite plane looks like that. I mean, that's the field coming off of an infinite plane. It's just uniform sigma over epsilon naught times 2. But as I said before, we're not just looking for the value. We're looking for how the function approaches that value. So, instead of taking z over big R to be 0, let's keep z over r in there, but replace the various subfunctions in here with their first order approximations. So I see two functions where z over r appears. I see this one and this one. Now this one is a single term, so the single term approximation of this is just z over r. This one, however, is a special case of x plus 1 to the power of n, where x is z squared over r squared, and n is negative 1/2. Now, of course, for anytime you see this form, the first term of this is just 1, because of course as x goes to 0, it just becomes 1 to the power of n, which is 1. So if we put in the first term, first order approximation, it's just 1. If this goes to 1, we can ignore it, and this goes to 0r, so it becomes 1 minus z over big R times sigma over epsilon naught times 2. Now that's much more interesting than what we had before. Much more interesting indeed, because we now know that not only is its value at 0, sigma over epsilon naught times 2, as it should be, but we know that it decreases linearly from that. It starts out at that value, and it just goes straight down. And that's much more interesting. We have more information here. So, for the other one, when we want to take z to infinity. Now this is my favorite part of the problem, and it's the reason why I wanted to do this problem on the board. Other students in the class came up to me, they didn't know what to do, and I showed them what to do, and it was really cool. So, now of course, we want to look at r over z this time. So we want to write this function in terms of r over z. So we're going to divide everything in here by z squared. And then take the z squared out front, or out back I suppose. Now this, of course, as we've done several times before, is 1 over z. 1 over z times z is 1, so this all goes away. Hooray for simplification. And we get this. Looks very nice. Okay, so obviously if we just substitute 0 in here, which is not taking a limit at all, this becomes 1, this becomes 1 minus 1, and the whole thing becomes 0. That tells us very little, in fact. We know that fields are supposed to go to 0 as they go to infinity, but we want to know the rate at which they go to 0. So we're going to do something like this again. But here's the thing. This time, we can't just take the first order, because that's exactly what we did. The first order approximation of this is 1, which is what we substituted it for anyway before, when we got 0. So we need to go one term deeper, as Leonardo DiCaprio would say. And the next term in this expansion is x times n. So x is this, so it's going to be because n is negative 1/2. So yeah, negative 1/2 goes into that and produces that. So now we get something a lot more interesting with much more information in it, which is 1 minus r squared over z squared times 2. 1 minus 1, 0, and then 0 minus negative, so plus this. Going to be that. So it's going to be r squared over z squared times 2. Right over here. Times sigma over epsilon naught times 2. And of course we can move this 2 over here as a 4. Now, this is of course much more interesting, But more importantly, we notice that there is a z squared in the denominator. And let's think about that. That's exactly what we should expect, because if we imagine that z is super, super large to the point where this disk is tiny, then the disk should resemble a point particle. For all intents and purposes, it can be viewed as a point particle. And so the charge coming off of it should, at sufficiently great distances, seem like the charge coming from a point particle. I'm sorry about that. I think my camera stopped recording for some reason. In any case, we want to make sure that these factors are correct. I really hope that I got everything. I'm going to have to watch that. Anyway, we want to make sure that the factors are correct, not just the exponent at which the force is scaling down. We want to make sure that the factors are correct. So we need to know what the total charge on the disk is. Well, total charge on the disk is going to be the area of the disk, r squared times pi, times the charge density on the disk segment. So that's just what Q is. So let's try to find Q in here. Well, we can of course multiply by pi over pi, because that's just 1. R squared times C1 times pi equals Q. So we can replace all of this with Q. And oh my goodness, 4 pi epsilon z squared. 4 pi epsilon distance squared. That's what we were looking for. The factors are correct. It behaves exactly as it should as it approaches infinity. The day is saved. I don't know, I think it's really cool. And I was really proud of getting that answer correct. And I'm really happy that I could demonstrate how to get that. And that's all I have to say.